Good morning, everyone. Okay, we're going to continue talking about hydrostatic forces today. Just as a reminder, your third homework assignment is due next Tuesday, so upload that to Blackboard before class. We're going to go through an in-class exercise today where I've actually printed out the problems in the same way that I often do for some other classes. Just as a reminder, the typical process when you are finding the magnitude of the hydrostatic force is, first of all, to look at the shape and try and identify where's the centroid for that particular shape. So the reason why we need to find the location of the centroid is that the magnitude of the hydrostatic force depends on that. And it's a little bit confusing sometimes, the fact that we're keeping track of two different distances. One of them being the depth of the centroid, and then the other either being a vertical or inclined distance to the location of the force application. But those are two separate distances, and we're going to get some practice working on that today. I haven't included the formulas on the paper here because I'm interested to know if it's already, just in the few short times you started working on it, if those formulas have and abbreviations for the variables, if that's sunk in. So what variable do we use to indicate the depth of the centroid? Delta H, right. And so what's the formula for finding delta H? Well, we just kind of do it by inspection, looking at the figure that's provided and the dimensions. All right. Magnitude of the hydrostatic force, so F is calculated how?
Pressure at the centroid times the area of the...
All right, good. Pressure at the centroid is P bar times the area. And how can we find the pressure at the centroid? Hydrostatic equation. So delta H times the unit weight of whatever fluid and the cross-sectional area. All right. 3, area moment of inertia. Now this one isn't rectangular. A lot of the shapes we've been using so far are rectangular. So what shape do we have here? Well, it's saying 2.764 meters from the front view. That gives us the width of it, but it looks a little bit weird, right? It looks like it's not circular, but that's just because this shape is at an angle. So actually, that is a circular object. It's just from the front view, its appearance is distorted. The projection of a circle that's at an angle looks like an ellipse. So if we go back to the area moment of inertia slide that we had at the beginning of class on Tuesday, we can find that area moment of inertia for a circle. Okay, so I about the horizontal axis is pi radius to the 4th divided by 4. Okay, so that's what you'll use there. And then finally, the location of the hydrostatic force. What variable do we use to identify that? YCP. And what does the CP stand for in YCP?
Center of pressure.
Center of pressure. And so the center of pressure is where the equivalent hydrostatic force is located. All right, so anybody remember what's the formula for YCP?
Is it the Y bar plus the moment of inertia over top of the Y bar times the area?
Good. Well done. That's exactly right. All right. So what's the difference between Y bar and delta H? Well, delta H is a vertical measurement from the centroid straight up to the water surface, and Y bar is starting at the same place at the centroid, but it's going along the inclined path to the surface rather than straight vertically up. So you'll have to differentiate between the Y bar and the delta H in this problem. All right, so let me hand out the paper for this one.
that thing. There's an acceleration on this earth when things fall.
All right, so I calculated the depth of the centroid a little bit differently than many of you. Many of you found the angle, the 53-degree angle that's inclined at, and that's fine. It's a perfectly good way to do it. I just was maybe lured astray by the 3, 4, 5 triangle and knowing that eventually I'm going to have the y bar anyway. So I calculated the y bar to begin with. I knew that half of that inclined distance on the plate itself would be its given diameter divided by 2, and then there's some unknown inclined distance from the edge up to the surface. So it's the hypotenuse where we've got 6 as the vertical component of that particular triangle. So through calculating the y bar, I then got the delta h through similar triangles. But even if you use that 53-degree angle, I think what you'll find is that the delta h, the depth of the centroid, straight up from the centroid to the water surface, should be about 7.11 meters. And I think that's really the trickiest part of the problem, is finding the depth of the centroid, because once you've got that, then the magnitude of the hydrostatic force is pretty easy. Just by sheer coincidence, it turns out our cross-sectional area is 6 square meters. And so if you multiply the pressure at the centroid by that area, you'll get 418 kilonewtons. Then step 3, area moment of inertia for the circular shape. We'll still have the same units for area moment of inertia regardless of what the shape is. It'll still be area to the 4th. And then the location of the force, the way that we identify where the equivalent hydrostatic force is located is the inclined distance from the water surface to the point of application. So the YCP here is just going to be the y bar that I calculated earlier. So yeah, any questions about this first in-class exercise problem?
Can you just go back up for a moment on the y for the y bar?
Mm-hmm. Yeah. So I guess it starts all the way up here. So the similar triangles relationship that I was using is that the hypotenuse of this triangle, the x, the unknown inclined distance to the edge, is to 6, as the vertical component 4 goes along with 6 in this triangle, and then the hypotenuse component 5 goes to x. So through that I got the inclined distance to the water surface and the edge is 7.5, and then I just added half of the diameter to that to get the y bar. Are there other questions?
What was the final answer again?
The final answer for the YCP, 8.936 meters. Okay, the next problem, we have a gate that's holding back water. The gate width is 2 meters, so that's 2 meters into the page. The height of the gate is dimensioned to be 6 meters. And we want to find out what is the force applied to the gate by the stop. So if you think about that, hydrostatic force is going to be below the center of area. So the centroid of the gate is here, 3 meters down from the hinge. The hydrostatic force is applied a little bit below that, and so it's causing the gate to rotate clockwise, where the stop is resisting that motion. So Same basic process to find the be able to do the moment analysis in the end. We want to start by finding the depth of the centroid, and remember that if we go straight up from the centroid, there isn't any water. And so how do we handle that? Do you recall what's the approach when, if delta H is supposed to be from the centroid to the water surface, so here's the center of the gate. If we go straight up, there is no water surface. So what did I tell you last time?
Think about it like there is water.
Yeah, just extend where the water surface would be, so that dashed line, and so you're measuring from the centroid to whatever elevation the water's at somewhere else, so over here. So that's how you'll do the delta H. Yeah, I think that's all I really want to say about this one before I turn you loose on it.
I told you it was.
Yeah, it doesn't work out as a chart. Water is called. So I understand that, but that doesn't make this.
Okay, so we find the depth of the centroid by looking at the geometry here. If it's inclined at 30 degrees, then that tells us that most of that 3 meters of length, the inclined distance from the hinge to the centroid is 3 meters. And it's only at a 30-degree angle, so most of that 3 meters is still going to be vertical. So multiply the cosine of 30, which is 0.866. So 86% of the length will be vertical. So 5.598 meters is the delta H. And if you like, you can calculate the y bar with the delta H, just having the delta H divided by the divided by the cosine of 30. You'll notice I found the inclined distance to the centroid a little bit differently. I said, well, it's going to be this 3 meters plus whatever the inclined distance to the surface is, and so I applied the cosine of 30 just to that vertical distance. But once you have the delta H, calculate the pressure at the centroid, magnitude of the force, and really what we're all headed towards is the moment balance, doing the sum of the moments about the hinge. And so I asked you not to calculate the YCP, but to find the distance between the YCP and the Y bar. So just in the YCP formula, moving the Y bar over to the left-hand side of the equation is going to give you how far below the centroid is the force applied. So you'll notice here I've got that gap distance between them dimensioned as 0.4641 meters. And that's useful because we can easily, just by inspection, see that it's 3 meters from the hinge to the centroid, and then an additional distance, that gap distance, down to the point of application. And then the block that's resisting the rotation, we know the moment distance there is 6 meters. So you should get the 380 kilonewtons as the force that the block is applying to hold that gate closed so that it doesn't open up and start spilling water. Do you have questions on this example? So we started with plates that were vertically oriented, and they're easy because delta H and Y bar are the same if it's vertically oriented. And then we talked about, if it's at an angle, how to calculate the hydrostatic force there. We can take it to an extreme, and we can say, what if we keep laying it down at an angle, more of an angle, more of an angle, and now what if it's horizontal, like is shown here? So what about the case of a plate that is 2 meters wide, 3 meters long, and it's horizontally oriented? So what we're going to do is we're going to consider this two different ways. And we'll calculate the hydrostatic force the same way that we have until now, which is just by considering what is the delta H, what's the pressure at the centroid, and so on. And then the other way of looking at it is what is the weight of the water that is above the inclined surface. So let's go through those calculations together. Yeah. All right. Find the force. The hydrostatic force is going to be P bar times A, which is to say delta H times the unit weight gamma times the area of the plate. And the centroid is in the middle, and so the depth of the centroid, the vertical distance from the water surface to the centroid, is just the 5 meters of depth that's shown there. And we're talking about water, so 9810 newtons per meter cubed for the unit weight, and then the area of the plate upon which the force is applied is 6 square meters. Okay, so the hydrostatic force, if we calculate it that way, is 294,300 newtons. All right, now what about the weight of the water above the plate? So what we need to do is we need to think of, what's the geometry of this box of water that's above the plate? And try and think in 3 dimensions. I'm really bad at drawing in 3 dimensions, but let's say that we've got a certain amount of water. If we go up to the surface, we want to know how much is that. So let's see, we have like a box of water, and it is 2 meters by 3 meters, and weight is volume multiplied by the unit weight. And so let me pause for a moment and have you calculate what is the weight of the water above the plate using this formula. Volume times the unit weight. Okay, so what's the volume of that box above the plate? And that's not an actual box. It's just there's a certain amount of water that's above it. And so the volume is going to be 5 meters of height multiplied by 2 meters of width and 3 meters of depth. So altogether that's 30 cubic meters. So there's 30 cubic meters of water above the plate. And if you multiply that by the unit weight, what you'll find is that the magnitude of the force is the same as the hydrostatic force that we calculate by using the approach of depth to the centroid, unit weight of water, and the cross-sectional area. So the conclusion that we can draw from that is that the vertical hydrostatic forces can be calculated by the weight of the water above a certain shape. And the reason why I bring that up is that we've only been working with flat surfaces so far. We're going to begin taking a look at curved surfaces and curved gates when we get together in class on Tuesday. And we have to have a new method for calculating the hydrostatic forces on curved gates. It's actually a 2-part process by which we're going to be looking at the forces coming from the side as well as the forces coming from above. And when we are doing those forces from above, it's all about the weight of the water above a certain object. So this is just kind of like your first taste of thinking about the weight of the water that's above an object. Any questions about this illustration? All right. Well, that's all I have for you today. Remember that the homework assignment is due on Tuesday. I've got office hours. If you've got questions, feel free to stop by. Otherwise, I'll see you then. Sure, yeah.